Let's try this again. All right, so we're going to go over the midterm, and then we've got our lecture on magnetism, starting magnetism today, and then some other activities. Probably we'll only have time to start lab 3 at this point because of technical difficulties. So your exam. So the first one are the conceptual questions, and I guess I'm a little surprised that you guys don't score higher on these because you have all of these to study from. So this is like your gimme question on the test. These come straight out of the lectures. So it's interesting because for my 223 class, where I give them an online activity each week, part of their midterm review is I just collected all of these multiple choice questions and put that on their review. And most people missed maybe one, but most people got 20 out of 20. And it's not my job to help you study. So this is your gimme question. If you guys aren't going through and collecting those concept questions and studying them, you should. There's really no excuse for missing these ones. That's like you already know those questions. So question number 2. On with the disappointment. This is a 2D vector problem. So this is review from 221. And I'm pretty disappointed that you guys don't remember how to deal with vectors in 2 dimensions. So you can pretty much guarantee you're going to see something like this on the final. And not only because I'm a little annoyed right now, but because magnetism is going to kick your ass. Magnetism is 3-dimensional. So if you don't know your vector shit, you need to come to my office hours. If you had trouble with problem 2, you need to come to my office hours because that is 221 stuff. How to deal with vectors, that's old hat, okay? So if that's causing you problems, today's lecture is going to kick your ass. I'm not even going to sugarcoat this, okay? Because today we're doing some really hard vector stuff, okay? And this class it's hard and it doesn't slow down. So I don't have time to do a stop, review, make sure we're all on the same page. We just have to go. So if this is your personal challenge for you, vectors, then please come see me. Wes?
Did you get them back?
Yes, I handed them back. So if you came in late, you didn't get it. Okay, so so that kind of covers what you should have not had problems with. Okay, so that kind of ends my my rant about studying things. Problem number 3 was hard for a lot of people. So I think for some people, some people need to review terminology and read the question carefully because some people weren't solving for the correct thing. So the question is asking for the electric field in parts A and B, solving for that, not the flux. And there are some pretty, what we call Lisa's theorem 1 and 2, can make this problem really easy. So for part A, if you're inside the shell, Q enclosed is just that single charge. So it acts like a point charge. So you can use your equation, electric field equation, for a point charge. Okay, so that's kind of logically making this problem faster. And then part B is the same thing, actually. If you're outside a shell of uniform charge, it acts like a point charge. So in part A, Q was equal to an electron, and in part B, Q is Q enclosed. So Q enclosed was the 350 protons sitting on the outside shell plus the electron on the inside for a total of 349 protons. Okay, so that, a lot of people didn't get that either. So that kind of caused people some difficulty in understanding there. Gauss's law is really the hardest thing we do before the midterm, so it's understandable that problem number 3 was pretty low averages, because that's just a weird topic and you probably won't have ever seen it in any other class prior to this. Problem number 4 was really similar to a homework problem, and I think for the part A, the primary difficulty people had was making the wrong assumption that the voltage across the capacitor is going to stay the same when it disconnects from the battery, and that's not the case. So the battery will charge up that capacitor with a certain amount of charge. That's the charge that it has to share when it's disconnected from the battery. So Q initial equals Q final. Q initial equals the first capacitor times the battery voltage. And then Q final would be the equivalent capacitance times the final voltage. And these two, battery voltage and final voltage, are not the same thing. The only thing that's the same is the charge that's happening on that first capacitor, and then when it shares that charge with the second capacitor. So when it shares it, CEQ is C1 plus C2, so that's splitting that charge up between the two capacitors. And so that's how you end up with V final is C1 over C1 plus C2 times V battery. So this is a fraction, right? And you'll end up with a lower final voltage than the initial battery voltage. So I think that kind of hurt people because they misinterpreted what's going to happen in that situation. And part B, I think people either know their terminology or they didn't. So if you know what I'm asking for, when I ask for stored energy, you did fine. And if you solved for something other than stored energy, then you lost a lot of points. So problem 4 kind of had a bimodal distribution. There was people who did really well, and there's people that didn't get a lot of points because they didn't solve for the right thing. Problem number 5, for the most part, you guys did really awesome reducing the circuit down. This one, I was going to say, this one had the highest score for any problem on the test. So for the most part, people did really well on this problem, which is good because this is kind of, for me anyway, this is one that can get a little tricky where you reduce the circuit down and then you kind of have to look at the reduced circuit and build it backwards back to the original circuit in order to solve for the current and the voltage across that R3 resistor. So I'm pretty pleased with how you guys did on problem number 5. And problem number 6, you guys picked up a lot of bonus points there too. So little mistakes here and there, but for the most part, people were able to get a few bonus points back on this one. So the average was 67.5%, which as low as that may seem is actually pretty typical for 222. This course is just hard. So hard. It is. 222 is the hardest of the 3 physics courses.
Oh, really?
It is.
I want to pass that last one.
That being said, it's not impossible. The highest score was 103.75.
Who's that? Who's that?
I can't tell you that.
You in this class?
In this class, on this exam.
Oh, probably the one that's not here.
So that's something to strive for, I suppose. So all right, so the solutions have been posted, so please take the time to look through the solutions and see where you went wrong. If you think I made a mistake on grading, please let me know. Yeah, Chris?
You say you want these back in a few days, or?
Just before the end of the term, yeah. Just, I'll hopefully remind you again, because I always am so terrible about asking people to turn those back. But you don't have to give them back today if you want some time to review what you did. Yeah, cry into your lunch. Any other questions about the midterm? No. This should be your wake-up call. This should be your wake-up call. And as I said, magnetism is harder. It's harder. So if you didn't do how well you wanted to do, then hit it harder. Hit the studying harder. And the final is comprehensive, so this stuff will come back and bite you in the ass if you don't know it. Thomas?
You said we're going to be doing more vector type stuff.
Yes.
How much would you say percentage-wise will be the final on vectors? Will it just be like one problem, or will it be much more dominant?
Pretty much today and next week is all vectors, so you can expect to see at least one, probably two workout problems that involve vectors on the final. And then we're starting thermodynamics after that, so thermodynamics doesn't involve vectors, so you're off the hook there, but the magnetism stuff is, it's very calculus heavy, so. Any other questions? I feel like a mom scolding my children. Okay, I printed off worksheets, so you guys probably got those, and the sign-in sheets up here if you haven't signed in. So just a quick overview about magnets. This stuff is stuff you've probably learned in elementary school at some point. So permanent magnets, these are materials that have some intrinsic magnetic field that doesn't go away. Usually it stays for a long period of time. And we talk about magnets in terms of their poles. So there's a north pole and a south pole. And you guys also probably learned this when you're little kids, that if you put the north and the south pole together, they are attractive, opposites attract. And if you put the same poles together, they repel. So south and south will repel, north and north will repel. And with magnets, any metallic metal, something like metal, will be attracted to a magnet regardless of which pole. So that's why we have magnets on our fridge.
Is that posted?
What's that?
Is that
The lecture?
Yeah, the lecture.
I posted it last night. Are you not seeing it? Oh, you know what I forgot to do? I posted it and then I forgot to make the folder visible. You don't see lecture 5? No. Okay. That's my problem. So I was like, I did it. I posted my lecture. I posted everything. It's just that that folder is invisible to you guys. All right, refresh. Do you see it now?
Yes.
Okay. Thank you for pointing that out. All right. Magnetism. So the first thing, we're going to kind of cover the same ground in many ways that we covered with electric fields and electricity. So the first thing we're going to talk about are magnetic fields. Magnetic fields use symbol capital B. They have units of Tesla, capital T. And a Tesla, you can break down into a Newton per Coulomb times meters per second, or a Newton per amp meter. And sometimes you'll see things in terms of Gauss. I don't think our book ever does that, but there's a conversion if you see a magnetic field in terms of Gauss.
Is this B or beta?
B. The Gauss unit was created a long time ago. So 1 Gauss was what they thought the magnetic field at the Earth's surface was. And that got abandoned when we realized that there's a lot of variability in magnetic field at the Earth's surface. So that's really not a good constant measure. So that's why 1 Gauss is just approximately the B field at the Earth's surface. So really, we don't just study straight magnetism. We're always studying electromagnetism because there's no pure magnetic particle in the world. Every particle that has magnetic properties also has electric properties. So how you create magnetic fields is one way to do that is moving electrons. So electrons have an electric charge, and once they start moving, just the act of them moving creates a magnetic field. So that's why we call this field of study electromagnetism, because there's always an electric component anytime we find magnetism. The only exception to that would be permanent magnets, just rocks sitting in the ground that have an intrinsic magnetic field without moving charges. But of course, we don't really do, problems that just involve straight permanent magnets, because that's not very interesting. So what else do I have to say? Yeah, I think I said everything. All right, so we learned with electric fields about equipotential lines and electric field lines. Electric field lines, just to review really quick. If you have a dipole, then we learned with electric field lines that they start on positive and they end on negative. So B field lines have similar properties. They're starting on the North Pole and they'll end on the South Pole. So in the picture on the board is a permanent magnet with the North and South Pole. And they've drawn the magnetic field lines for a real permanent magnet, where you can see a lot of fringing of those field lines. So that's real field lines. And if we do an ideal permanent magnet, just to give you a comparison, you'd have, you basically can idealize those lines as being perfectly parallel on the inside with no magnetic field out here, which is very, very idealized, but nevertheless. So up here, B would be 0, and B would be 0. And you can see in reality that's not the case, but your B field is going to be a lot smaller on the top and the bottom than coming out of the front of the magnet. Just like with the electric field lines, the narrower your B field lines are, the stronger your magnetic field. And then the weird thing about, well, and I think this is true with electric fields too, is that all the lines are closed loops. So you see this one kind of disappearing off the page. It's looping around and it'll eventually connect. And the one that's perfectly straight, to kind of use your imagination here, this line would go off into the infinite universe, circle back around at infinity, and come back and make a closed loop. So that's magnetic field lines. The magnetic field of the Earth looks something like this. If you can't see this picture very well, this is North America and this is South America. You'll notice that the field lines here make the Earth sort of act like a bar magnet with the South Pole on top and a North Pole on bottom. This is super confusing for students. So what we call the North Pole is actually the magnetic South Pole of the Earth. And to avoid confusion, I'm going to talk about what we normally call the North Pole as the place where Santa lives. Because if we call it the North Pole, that's confusing now because it's actually the magnetic South Pole. And then the place where the penguins live, Antarctica. Antarctica is actually easier than saying where the penguins live. Antarctica would be the magnetic North Pole. So what's interesting is when we have solar flares, and we just had a really big solar flare and it knocked out some of our satellites for a little while, the radiation, the solar radiation coming from the sun is really damaging to electronics and our bodies. So when there's a big solar storm, they actually divert planes that typically will fly straight over the North Pole to save time. Like if you're going to Russia, you're going to skirt over the top of Alaska. they'll actually avoid going that pathway because up here, you're going outside of this short shell, this magnetic field shell, and you're exposed to solar radiation. If there's a lot of solar radiation because of a solar flare, then your body is being exposed to all that. It's like going into an X-ray machine. So it's really bad for you. So if we didn't have a magnetic field on this Earth, we wouldn't exist. We would just, like, you would basically be born and you die of cancer before you reach the age of 1. So not all planets have magnetic fields. In fact, Mars doesn't currently. So if we ever send people to live on Mars, they're going to have to create shelters that are shielded. Otherwise, they would just be exposed to tons of radiation all the time. The aurora borealis effect is actually those solar photons from the sun will hit a magnetic field line and start spiraling down the magnetic field line. And that's literally you seeing the Earth protecting you from the solar radiation. So those solar photons will spiral down the field lines and then go into the South Pole. And where you get a whole lot of those collecting together, where the B field lines are really close at the North Pole, where Santa lives, is where we see the aurora borealis. In fact, they see that same effect in Australia and stuff. I don't think they call it the aurora down there. They call it something else, aurora or something.
The lights are actually visually seeing the magnetic field.
Yeah. So that's these long streaks. That's actually the field lines. So it's not like the picture here where it shows them nice and straight. The field line can be a little wobbly. And that's why the Earth's magnetic field isn't constant at all points on the surface. It's a little wobbly.
So, question before we move on. So you're saying that the magnetic field reflects photons?
It doesn't reflect, it collects them.
Okay.
It attracts them, yeah. So it will attract them to the field line and then they'll spiral down the field line instead of coming through the field lines and striking the Earth.
And so that's why at the North Pole, it all comes down into the Earth because the field lines.
At the magnetic North Pole, which is Antarctica.
Yeah.
Yes, yeah.
Yeah. Okay. Well, at both poles. Wouldn't it be at both poles?
Well, it leaves the North Pole. It leaves out of. Oh shoot! See, I've got this all mixed up because this is labeled north. Yeah. So this is actually the magnetic North Pole. So the photons would actually be spiraling up and then entering at where Santa lives. Yeah. Yes.
Because I was going to say, it would actually, the magnetic field, wouldn't it be stronger at the top because the lines are closer together?
Yeah, the magnetic field should be the same magnitude at the top and the bottom. It's just that it's exiting out the bottom of the Earth and entering at the top of the Earth. Mm-hmm. Of course, some of the radiation gets through. Actually, quite a lot of the radiation gets through. Otherwise, we wouldn't be able to grow anything. And that's why we have to wear sunscreen, especially me. Okay, so that's magnetic field, and magnetic fields create a magnetic force. So magnetic force, we're going to put F sub B, so we know it's due to the magnetic field, and it's a force, so it has units of newtons. And any electrical charges that are moving in a magnetic field will feel a force. So if you have static charges not moving in a magnetic field, they won't feel a force. So a permanent magnet, of course, is made out of atoms, and atoms have electrons. If they're stuck inside their atom, so they're not moving, then the magnetic field inside that magnet isn't going to cause them to start moving around in that magnet itself and creating current flow. So they actually have to be moving first in order for them to feel a force due to the B field. And we will hammer this idea dead into the ground by the end of the lecture. Now comes the really hard vector math. The equation for magnetic field includes a cross product. So we're going to review our math about cross product here. This is just as bad of a marker. So it's the charge, whatever electric charge that's moving, the speed with which that charge is moving, crossed with the magnetic field that it's in. And that will give you the force that that charge feels. This is not a multiplication sign, and not in the traditional sense. It's a way to multiply vectors. We've learned about dot product. Now we're learning about cross product. So let's do our cross product review. Okay, so I think I'll come back to this slide and we'll talk about this equation more, but let's do a review here. So if you have some vectors, A and B, and you decide to cross them, do a cross product with them. So let's say A is in this direction and B is in this direction. Just not do three-dimensional right now. The result of doing a cross product we call vector C, and C will be perpendicular to both A and B. So we're going to learn how to do this. I'm going to get my right hand out. A, B. Okay, so C, the result of those doing that cross product is going to come out of the board. And to draw a vector coming out of the board, we do a circle with a dot in it. So that's a vector coming out of the board. And this is not commutative. So if I said B cross A, that would be a new vector, D. We'll do our same B and A. And that would create a vector that goes into the board. So why the dot and why the cross? It's like an arrow. So vector looks like an arrow. So if you looked at an arrow on end, it looks like a point. And if you're looking at the back side of an arrow, you'd see the feathers, the fletchings. So it looks like a little X. Okay, how this is actually defined in math land, you've got vectors A and B, which have X, Y, and Z components. AX, AY, and AZ. And then vector B would have BX, BY, and BZ components. And when you do the cross product, C, this marker, can be found by putting A and B into a matrix. So our unit vectors for the X direction, Y direction, and Z direction are I hat, J hat, and K hat. And then you collect things that are for the X direction, the Y direction, and the Z direction. So we've got AX and BX, AY and BY, and AZ and BZ. And actually doing the cross product on this matrix, my math teacher, my calc teacher, called it ninja math. You guys ready for some ninja math? You're going to love this. All right, so what this equals, first you get the component of C in the X direction. So I hat. So in order to get I hat, I'm going to cover up the I hat column, and I'm going to look at this 2x2 matrix that's down here below. And my ninja math goes like this. Everyone watching? Hi-ya! That's right. That's right. this times this minus this times that. I know. That's so Jordan can enjoy it later. He doesn't fall asleep. All right, so that was AY times BZ minus AZ times BY. All right, and then to get the J hat direction, this is really weird, but if you had many, many directions, like if you increased your matrix to